Everyone, welcome to the today's class. It's a very important class. It is on stereochemistry. Okay, stereochemistry is how the molecule looks three-dimensionally, and here we'll be talking about what is called as superimposability, and then we'll talk about the two very important terms, what is called as enantiomers and diastereomers. Okay, so let's first talk about superimposability. Now imagine this palm is there. This is my left hand, this is my right hand. Imagine if this molecule, palm is in two dimension. What I'm trying to say is, we are not looking at the depth of the hand. I'm just looking at the frontal surface of it. And this is my right hand. So I'm looking again at the superficial front of my palm. Now these two palms exactly fit on each other. This is called as superimposable. So these two palms are superimposable if I am talking in terms of two dimension. But when I am considering a three dimension, then I have to look at the depth of it. So now you see, if I put it like this, this does not exactly fit in that, because it's different, depth is different, the shape is different, it will not exactly fit in. So that means this hand and this hand is different. So now this hand is exactly mirror image of this. You see, when you see a mirror, what do you see first? You always see the nose first, because nose is front, and then you see ears behind. Similarly, if you see this, so fingers are front, so if I put a mirror here, I will see a finger here. Then what do you see? That they both are exactly mirror image of each other. So they are isomers which are mirror images, but they will never ever superimpose on each other. If I fit in like this, my thumb is going here, my thumb is going here. If my thumb was this side, my thumb was this side, then it would exactly fit. But here you can see my thumb is this side, this thumb is this side, does not fit in. If I put in like this, then also they don't, because their shape differs. Another nice example to look for the enantiomer will be, if you look at car. Imagine looking at the Indian car and an American car. So what is the basic difference? I am telling you, take a car which of the same company. Okay. Now there is a car of Indian company whose driving seat is on right side. That's how it is always. But if American car is there, the driving seat will be on the left side. Now if you put them next to each other, then what do you see? That they are mirror images. Here you have the driving seat of the Indian car, and next to which is the driving seat of the American car. If you put front of them also, then you will see that they are mirror images. But whatever you do, how much ever you rotate, you will see that they do not sit on each other. They are not superimposable. So such molecules, when I talk about small molecules, such molecules which are mirror images, okay, which are mirror images to each other, they are stereoisomers which are mirror images to each other, but they are non-superimposable. They are called as enantiomers. Okay. So for enantiomer to happen in organic chemistry, the molecule should be chiral. What do I mean by chiral is, there should be no plane of symmetry. The molecule should be completely asymmetric. We'll come to it. What do I mean by that is, these two, American car and Indian car, they look exactly same. They are just mirror images of each other. Just little difference is there. Now, if I put both of them on same field, then you cannot make out the difference. Both will run in the same speed. Why you cannot make out the difference? Because though these two have directionality, the field does not have directionality, and therefore field does not have the capability to differentiate between them. But imagine I put them on a road, Indian road I put. What will happen? Indian car will move faster, American car will not be able to move faster, because Indian road also has the directionality. So when I am talking about the chiral molecule, when I am talking about the enantiomers, if I want to separate them, if I want to differentiate them, I need a system which also has directionality. Pretty much like you are having left hand and you are having left hand glove. Now left hand glove will exactly fit in the left hand, but that left hand glove will not fit in the right hand. Why? Because the glove also has directionality. it has the left and right sense. So left fits in left, but left does not fit in right. Right? Then there is another concept which will come, which will be called as diastereomers. So what is diastereomers? Diastereomers are stereoisomers which are non-superimposable mirror image. Don't worry if you don't understand this, we will deal with them greatly, but just a little idea about it right now. So diastereomers are stereoisomers which are not superimposable to each other, and they are also not mirror image to each other. Now imagine two Indian cars are there, but in one car I remove the behind bulb, the red bulb, and put on top of it. So when I put on top of it, what happens? Now the shape has changed. Now it is still the same car, it is still isomer because I have not changed any part. All the parts are same, just one that behind red light I put on the top. So now because it is on top, it is neither mirror image. Of course now they are not superimposable. Now if I put them on road, the light which I have put on top, that car will start moving very fast. Why? Because now it has become VIP car. On VIP car we put on red and it moves very fast. So like that only, diastereomers are stereoisomers which do not have, which are not mirror images and are not superimposable to each other, and they have different physical properties. So it's very easy to separate them out. Okay, we don't need special directionality on the same normal road also, but you can separate these two cars. Let us look at it. So for a molecule to have these stereoisomers, what we need is chirality. So what is chirality? Chirality means a molecule is there, it should not have plane of symmetry. A simple way to understand will be, if a carbon atom is there, the carbon atom should not have plane of symmetry. For that to happen, it should have all four substituents different. Let us see this molecule. So this is a molecule, it has four substituents, 2 hydrogens, 1 methyl, 1 ethyl. Now this molecule has 2 same substituents. This carbon has 2 same substituents. So there is not one carbon present here which has all the 4 substituents different. So this molecule is not chiral because this molecule has plane of symmetry. What is meaning of plane of symmetry? That means there is a plane, plane just a line, which not a line, it's a plane, it's like a board, cardboard which cutting across. And if I see from the board, if I see other side, exactly see the same thing which I see on the other side of board. Imagine I'm cutting it with something like that, one board is there. Then what happens? If I move little, I see hydrogen. On the other side of board also, if I move that much, I see hydrogen. If I see here, imagine this methyl. Methyl is a ball. Half of the ball is this side, half ball is that side. Similarly, ethyl, half ball is down, half ball is up. So on the either side of the plane, it is exactly same. So it is having plane of symmetry. So this molecule cannot have stereoisomer. How do I know? Let us draw the mirror image of it. So I am going to draw a mirror image here. Mirror I have put here. Now I am going to draw the mirror image. So as I said previously, when you look at the mirror, what do you see first? You see your nose first. So it is coming here, methyl is coming front and ethyl is coming behind. I hope you understand this shape. How it is shaped? This hydrogen and this hydrogen, they both are on the board. This methyl is little down, but it is towards the viewer. You are the viewer. So towards outside the board. And this methyl is same angle, it is behind the board, so it is away from the viewer. Now when I draw this mirror image, I'll see this carbon and I put hydrogen here, and this hydrogen which is behind, you see your ears are behind. When you see in the mirror also, ears are behind. So this hydrogen is also behind, and this methyl is towards the viewer. So here also you draw methyl towards the viewer. And this ethyl is away from the viewer. Now it looks like these two molecules are mirror images. and doesn't look very symmetric. It doesn't look like they are superimposable on each other, because if I pick it up here and put it on here, they are not superimposable. But imagine I hold this molecule. This imagination is very important. Please pay a lot of attention to this. I am holding this hydrogen. I am holding it and just pulling this bond and rotating it 180 degrees. It's like fan, you understand? So this hydrogen is the pole through which this fan is hanging down. So this part is down like that, and this hydrogen remains here, but this whole bond rotates. So this whole thing rotates. So what I am doing is holding like this and catching this hydrogen, rotating it 180 degrees. So what I am getting is this hydrogen, if I put as H1 and H2, H1 remains up and H2 has gone on this side, right? H2 has gone on this side. Now, when I rotate 180 degrees, this methyl also has rotated 180 degrees. So this methyl, which was front, when it rotates 180 degrees, it goes behind the board. If you don't understand, please think about it, then only move forward. So you are having this methyl behind, and what happens to this ethyl? This ethyl was behind, it rotates 180 degrees, it comes front. So you are having ethyl group here. Now you look at this molecule. Okay, now this much you have done, you got this. Now what you do is we'll rotate another 180 degrees. Okay, I'm just taking this molecule, rotating it 180 degrees. So then what happens when I rotate another 180 degrees? So this H2 goes in place of H1 and H1 comes in this place. You understand it is how it is. It's like this. This index finger is H1 and thumb is H2. I'm just rotating it like this, so that H2 goes in place of H1 and H1 comes in place of H2. So when I do that, what I'm getting is H2 here, H1 here, and then when I am rotating, what happens? This ethyl goes behind the board, methyl goes front. I hope you understand. This thumb was the ethyl part, which is front of the board, and this methyl is away from the board. I'm rotating 180 degrees, so methyl comes front and ethyl goes behind. Okay, now look at this molecule. Now this H1, H2 will remove because finally they are hydrogen. Now if I pick up this molecule and put on top, imagine I'm just picking it up and putting it like this. This hydrogen exactly fits on this hydrogen. This hydrogen exactly fits on this hydrogen. And this methyl, which is front, this methyl is also front. So it exactly gloves in, and this ethyl goes inside. That means these two are identical. So though I drew the mirror image, the mirror is nothing but the same molecules. So they are not stereoisomers. So very important point. For stereoisomerism to exist, molecule should have chiral center. So for a chiral center, that means the carbon should have all the four substituents different. There are some molecules without chirality also they exist. I'll come and I will talk about it because they don't have planar symmetry. But in general, as you saw, if it has two same substituents, then chirality does not exist. Now imagine if I am putting here OH. I am putting here OH. Now what happens? Now this carbon is different. It has all four substituents different. One hydrogen, one OH, one methyl and one ethyl. Now let me draw the mirror image. So when I draw the mirror image, what I am getting is H here, OH here, right? Let me do all the operations which I did in the previous molecule. So now what I did here, first I rotated 180 degrees. So I am rotating here also 180 degrees. So I am getting OH here. Okay, now let us go step by step. Now are these two molecules superimposable? Right now we don't know exactly that they are not superimposable. If I fit on this also, it does not fit in because this side OH is this side, this OH is this side. Now if I lift this molecule and put on top, this H fits on this H, this OH fits on this OH, but outside is ethyl on this and outside is methyl. So methyl and ethyl will not superimpose. So of course these two are not same, right? So now let's do the other operation which we did. We are lifting this molecule and rotating 180 degrees from here to here. Then what happens that OH comes here and H comes here. Now this methyl and this methyl superimpose. This ethyl and this ethyl superimpose. But this hydrogen, this OH are not superimposing. This OH and this H are not superimposing. Okay. So basically what we are saying is these two are two different molecules. They happen to be mirror images. Not that whenever molecule comes, then mirror image comes and then they are two different molecules. Not like that. If a molecule has a chiral center, it has four different substituents. It has chirality, it has directionality. And because of directionality, even if one substituent is here to there, if a substituent is changed from here to there, we are getting a completely different molecule which has different directionality. And because they are two different molecules, it should show some difference. Okay, it should show some difference, and that difference is seen in optical activity. I'll come to it, but before that, let me say a few things. So what I'm saying is this molecule has chirality. What is its enantiomer is basically, if imagine this bond, one of them has broken. My hand has directionality actually. If I remove this hand and put it here and put right hand on the left hand, now this is different. That this Govin and after breaking my hand and exchanging, they are two different. They are not exactly the same. So similarly, I break any bond. Imagine I break this hydrogen and change with ethyl group. So I am putting hydrogen, I am putting here. Sorry, here already it was hydrogen. So I am exchanging. So here I am putting ethyl and here I am putting hydrogen. Now what I am saying is, because it has one chiral center, it has one chiral center. So it has only two possible stereoisomer. So when I do that, I am getting stereoisomer. I am getting the enantiomer. That means this and this are exactly the same. Okay, this and this are exactly the same. Right now this is not like looking like mirror image. This molecule is not looking like mirror image of right now this molecule is not looking identical to this, but we can show that this and this is same because this is the mirror image of the starting material. Let me draw the starting material once again so that we don't get confused at any stage. Okay, these two are mirror images. So that means these two also should be mirror images. Right now this and this are not looking like mirror image, but this is also a mirror image. If I change it properly, you can see that these two are mirror images. So very important to understand this point. If it is chiral, it will have two molecules. There are two stereoisomers which happen to mirror images and they are called as enantiomers. So these two molecules, how do I do it? So that I can start looking at as if they both are mirror images to each other. One simple thing what I can do is, let us put this OH on that side because that's what a mirror image looks like. OH is behind, so this OH is behind. Okay, so I am holding this part, and at the end this both will start looking same. We'll find out that. I am holding this ethyl part. I am rotating it 180 degrees. You understand? This is like fan, that that pole. I am holding that and it's rotating. It's a fan. These three blades are there, so they're just rotating. So this rotates 180 degrees. So what do you get? You get ET here, you get carbon here, you get OH here, and then 180 degrees it has rotated. This rotation is very important. This rotation is very important every time you have to do. So this hydrogen which is behind the viewer, it is away behind the board. When it rotates 180 degrees, it comes front of the board. So what I am getting is H is front. What I am getting is H is front. H is front, and this methyl is going away from the viewer. Okay. Now this part looks like mirror image, but this part doesn't look like. So what I am going to do now, I am going to rotate it again so that hydrogen comes here. So I am going bond by bond. Simple way will be to look at it. I am holding this OH. You You understand? Now this OH is the pole of the fan, and these are the three blades. Now I'm rotating exactly 60 degrees. What I'm doing is basically I'm holding this and rotating it little bit so that this hydrogen comes in this place of ethyl. So it's like this, you understand? This thumb is hydrogen, this index finger is ethyl, and this middle finger is methyl. So hydrogen is towards the viewer, this hydrogen, this thumb, this methyl is middle finger is methyl away from the viewer, and this ethyl is in the plane. So I'm rotating it 60 degrees. So when I'm rotating 60 degrees, what is happening? Hydrogen is coming up, ethyl is going back, and methyl is coming front. Think about it. What I have done is I have held this so this OH does not change the place. I am rotating it. Hydrogen is coming here. So hydrogen is coming in place of ethyl. Ethyl is going behind. So ethyl is coming in place of methyl, and methyl is coming front. It is coming in place of hydrogen. So what I am getting is another operation. What I am getting is OH remains here, H comes here, and methyl comes front, and ethyl comes behind. Now look at these two and look at these two. These two are exactly same. That means this is the enantiomer. So this is exactly same as previous one. Okay. So now look at this. Now these two are mirror images. So if any bond is broken, if any bond exchanges the place, you will get enantiomer. Now if I again break any bond, it will come back to original, because if one chiral center is there, only two stereoisomers are possible. It is called as enantiomers. So simple formula is there. You have to remember this formula. Number of stereoisomers possible in a molecule is 2 to the power n. So what is 2 to the power n? Number of stereoisomers possible. 2 to the power n, where n is number of chiral center. So in this molecule there is one chiral center, that means one carbon is there where all four substituents are different. So number of stereoisomer possibles are only 2 to the power 1 is equal to 2. So it has a pair of enantiomers. So any bond you break, it becomes enantiomer. Again you break, it becomes same thing again. Again you break, again it becomes enantiomers. So these two enantiomers are non-superimposable mirror images. Now what happens is, if these two are two different things which just now we saw, for 100% we confirmed because they are not sitting on each other. So if they are not sitting on each other, they are two different stereoisomers. So they should show some difference. And the difference is, since they will have exactly same physical properties, same chemical properties. What I am trying to say is, if the molecule on the left and the molecule on the right, which we saw they were mirror images, they will, if this has 60 degrees boiling point, that also will have 60 degrees boiling point. If this has certain amount of polarity, it will have exactly same amount of polarity. You cannot separate them. Basically when you do separation, we generally do column, and column separation is basically depend on the polarity. Exactly polarity are same, you cannot separate them. Their chemical property is same, they both react exactly in the same way. Unless I react with some other chiral molecule, and then they'll start differentiating a little bit. But yeah, their NMRs are same. So even if you have two different enantiomers, if you do NMR, they will show exactly same NMR. You do any instrumental analysis, all of them will show exactly same. You cannot differentiate between them. But just now we saw that there are two different molecules. So it should show some property different. One property difference is in the body. You know, in the body, if you take these molecules, one may act as a good drug, the other may act as a poison, because body has enzymes. Understand? Body has enzymes. Enzymes also are made up of chiral molecules. All amino acids are chiral. So when you take, they start differentiating between these two drugs. They start differentiating between these two enantiomers. So one of them, it may react one of the enzyme will react and it gives you good effect as a medicine, and when you take other one, this enzyme will not react because it has different directionality, and some other enzyme will react with it and it will become poison, right? So what we need is, and what difference we see in the lab is these two have two different optical properties. So when I drew this, so these two are two different molecules. They are not superimposable on each other. They just happen to mirror image. Okay, mirror image is not such a big thing. Somehow people get confused. No, first you draw mirror image. No, just break a bond. They will be mirror image. Okay. So when you see these two molecules, they have different properties. So the difference in properties in optical activity. If I make solution of both of them separately and I put them in polarimeter and I pass plane polarized light. Plane polarized nothing but light is there. It has in one plane all of the light radiation side one. So one of them will rotate in the left direction, the other of them will rotate in the right direction. By looking at the molecule, I cannot make out that which will rotate left, which will rotate right. That's not possible experimentally, but you'll always observe that one of them will rotate in left and one of them will rotate in right. Imagine this rotate the plane polarized in left direction. So we call them levorotatory, and this one, imagine if this one is rotating left, so this has to rotate in right direction. There is no other option for it. Okay, and so this will be called as dextrorotatory. An interesting thing is, if this rotates the light in the left direction to 18 degrees, so this will also rotate the light in the right direction again in 18 degrees. So this is also 18, this is also 18 degrees. Just for our convention, for the levorotatory we say minus and for dextro we say plus. So this is rotating the light in minus 18 degrees and this is rotating light in the plus 18 degrees. Plus and minus, just that. Minus means in the left direction, plus means in the right direction. So this is the basic property of enantiomers, and in next class we'll see about diastereomers. Okay, thank you.